So, what we will do next is to see the presence of a three-fold axis. We saw it already with a different diagram, of course there we had different objects, but in this particular case we have a three-fold axis. Now the three-fold axis is illustrated with respect to the presence of a two-dimensional motif having a three-fold axis. Now here I want you to carefully observe this and identify the nature of the three-fold axis. There are again, just like in the two-fold axis situation, we have to put the objects in such a way in this particular motif that they are related by three-fold symmetry. So, if they are related by three-fold symmetry and we still demand the close packing, then we have in this particular case three types of objects, the one in red, the one in white and the one in black. So, three objects, and now I am marking the 0 0 of the three-fold axis at this position. I will call it as the origin. So, you see that at the origin there is a three-fold intersection of this. Go back yourself and go to that previous diagram, which I think I will show you again. We had this picture, we saw that there is a three-fold axis which now relates these three objects, the three fish. We also have the relation of the three birds. We also found an additional factor, that is the presence of the six-fold arrangement of the tortoise, but then the tortoise are arranged again with respect to this three-fold. So, I have taken this example, which is a much simpler example to illustrate the same. You see that they are identical objects here, they are not different kinds of objects, except that the colors are coded differently, showing that the orientations are different, let us say. So, as a consequence you see that the presence of these three fellows with their tails intersecting at the three-fold and the presence of these three white ones with the nose intersecting, they generate a three-fold. And if you now look at the black positions 1, 2, 3, 4, 5, 6, they are six-fold related, and the three-fold relation is observed with respect to the three black ones here. So, there are two types of possible three-fold rotations which can generate this motif, and therefore, it is not just the three-fold rotation at the positions where we have, this is different from the previous case where we had this lizards. Here again you see that the two-folds, the job of the two-fold rotation is the same, to rotate the object by 180 degrees, but the object orientation decides how the objects themselves orient. For example, in this case the noses were related by two-fold, in this case the legs were donated by two-fold, and here the elbow joints were related by two-fold. And similarly, in this particular case you see that the relationship with respect to the black representation of the object is a three-fold representation here and a six-fold representation here. So, remember the three-fold and the six-fold go together, and in fact this is something which we will observe even in 3 dimensions, and therefore, we will get very special cases of the nature of the unit cell when we go to systems which we are going to define later, called the trigonal system and the hexagonal system. And this is the kind of origin to the existence of them together in a given unit cell. So, you see with 2 dimensions what we have tried to do so far is to understand the concept of two-fold, the concept of three-fold. We can also introduce the concept of four-fold. Just like the three-fold and the six-fold existed together, we also have the four-fold and the two-fold existing together in this diagram. This is again a different kind of lizards, different sets of lizards we have shown here, and you see that the tails of these three fellows intersect at that point, the tail of this, tail of that, tail of this. There are 4 of them now. The angle between them is 90 degrees, and so this particular unit cell which I have marked is a unit cell which is a square. Earlier the two-fold unit cell was a rectangle, the three-fold unit cell was whatever we had before, that is representing the three, it was a trigonal unit cell. Of course, we are talking about 2 dimensions. So, in 2 dimensions it has a three-fold symmetry, it has a six-fold symmetry. So, three-fold symmetry, six-fold symmetry, four-fold symmetry and two-fold symmetry also decides what should be the nature of the lattice, what should be the nature of the unit cell. So, that means if A is equal to B, okay, if A equals B and angle is 90 degrees, then you have what is called as a square lattice. Okay. So, the square lattice now can be unique in the sense that we have the fourfold symmetry. Once we have this symmetry present here, we will get the presence of the fourfold symmetry here as well. But apart from that, we will now generate the twofold symmetries at these points. Just like we had 3 and 6 there, we have 4 and 2 here. So, the presence of the twofold is inherent in a square lattice, but the fourfold now dominates by occupying the unit cell edges. Now, these are take home points. At this particular point, we are not making any statements or final statements, because we are studying number 1 the objects in 2 dimensions. We are looking only at projections, and the second one is we are now looking at some abstract objects. We are going to replace these with molecules later on and look at the molecular symmetry, how the molecular symmetry and the crystal symmetry accumulate together. Just to make life easier at this particular moment, we see that this fellow, this lizard, has no symmetry. And even though the lizard does not have any symmetry, the way in which it gets arranged in this lattice produces these 90-degree angles. So, we have this 90-degree angle because of the presence of the lattice, and therefore, these objects which have no symmetry by themselves can use this fourfold symmetry and arrange it themselves in this. Some time ago, there was lot of work done and imaginations flowed. People imagined various things of how to arrange objects into different kinds of unit cells and so on. And there was a person by name Kitai-Gorodsky who found that if the object itself has a certain symmetry, suppose this object has a fourfold symmetry, suppose instead of the lizard we have a cubic block, okay, and then we now look at the projection down the given axis. Let us say it is projected down the cube axis. Then he says he found out that if you examine a large number of such objects, if the molecule by itself has a symmetry, the molecular symmetry will be utilized by the crystal symmetry. So, when it goes into the crystalline lattice, when it goes into this unit cell, the unit cell will now ensure the presence of the molecular symmetry. That means, we now not have 4 of these, but your cube is bound to sit here at this point. We have also made a remark that each and every point in this particular case will have the cube. So, this will also have the cube, this will also have the cube, this will also have the cube. So, that means the molecule now becomes special. We call these as special positions. And we will be going into the more details once we understand this symmetry fully, we understand the basics of symmetry, and then we understand how translational periodicity and symmetry can be combined, and how the various crystal systems can be generated, and therefore, we will put all those restrictions together and talk about the general positions and special positions when we derive the space groups in a much later class. So, at this particular moment, we see that if the molecule has a symmetry, Kitai-Gorodsky's finding is that if the molecule has a symmetry, the same symmetry should be maintained in the lattice as well. So, this particular 2-dimensional lattice should have that symmetry if the molecule has that symmetry, in which case the packing becomes compact. Then only we will have the closed packing of these objects in such situations. On the other hand, if the object is not having the fourfold symmetry also, or any kind of symmetry, as in this example where there is a lizard sitting here, if they are arranged in such a way that there is a fourfold symmetry, then the fourfold lattice can be fitted on to this particular system. So, the objects now are sitting what we call as general positions. They are sitting in what we call as general positions. So, just to tell you about this a little more detail, we now have to derive the so called equivalent points. So, in the twofold rotation, we got x y z and x bar y z bar, and then we have to now look at what happens when we have a fourfold symmetry, what happens when we have a twofold symmetry, and so on. So, this is the next step to which we go, and the step which we take up to do that will come a little later, because I want to introduce you to the opposite congruence objects. See, so far we have looked at only the direct congruence objects. So, the objects of opposite congruence, and I am giving you an example from literature and that of a molecule. In this particular case, I have shown the molecule ferrocene and not ferrocene, this is diphenyl iron, it is not ferrocene. Ferrocene will have a 5-membered ring system. This has a 6-membered ring. So, we have the diphenyl and iron is at the center. Now, the way the molecule appears, the molecular symmetry appears, is the presence of given any x, y, z, it can go to minus x minus y minus z. So, this is an inversion symmetry. Center of symmetry, we call this as the center of symmetry being present at this particular position. So, the molecule is centrosymmetric. So, by the logic which we use now so far in case of direct congruence objects, if the molecule is centrosymmetric, then the molecule has to go into a crystal system which is also centrosymmetric. So, the lattice it chooses should also have a center of symmetry. Not just that, the lattice it chooses should have its center of symmetry coincident with the center of symmetry in the molecule. So, the molecule has a certain symmetry and there is no further freedom given to the molecule. The molecule still sits in a position with which it will generate the center of symmetry. So, the molecule symmetry and the lattice symmetry will have to have a center of symmetry, because the space in which this molecule is now going to be put, either it is 2-dimensional or 3-dimensional, will have x, y, z to minus x minus y minus z. Every point in this space will be going from x, y, z to minus x minus y minus z. So, the molecular symmetry therefore dominates. This is how Kitagorowski observed it. So, I thought I will give an example with a object of indirect congruence. Object of opposite or indirect congruence can also have mirror planes. This is an example where Escher's diagram again I have used in order to illustrate the presence of a mirror plane. You see, we talked about points, centers of symmetry. We talked about axes of rotation about which the rotation takes place, 2, 3, 4 and 6, 1, 2, 3, 4 and 6 are the axes of rotation. We have the point of symmetry which is the center of symmetry. In this particular case, we had this molecule just now discussed, the iron compound, where iron is sitting at the center of symmetry. So, we have the rotation axis and points, as we said in the very first class, that we have symmetry elements which can be points, which can be axes, which can also be planes. So, this particular plane is a plane which is now defining the x, y, z. If we define in this particular way in which we have shown here the coordinate system, you see that there is a change in the y axis, in the y direction. So, x, y, z has gone to x minus y, z. So, what happens in this particular case is that there is a plane which passes through this center of this beetle, and you see that the right hand side of the beetle is identical to the left hand side of the beetle, and this goes through the entire motif, and so we define what we call as a mirror plane. So, this mirror plane is now in the plane of this is the y direction. So, the mirror plane is coming in such a way that we also invoke the presence of mirror planes with the other object, which is now the black object, the black beetle, that also is related by a mirror plane. This also is related by a mirror plane. So, the mirror plane propagates through the entire lattice, generating a closed packed motif. So, in this particular case, what is required is in case of the center of symmetry, we needed a point. Here we in the case of the rotation axis, we need an axis of rotation about which the rotation occurs. It could be a 2-fold, 3-fold, 4-fold, 6-fold. Whereas, in this particular case, mirror stands out by itself. So, in this case the mirror is perpendicular and we call it a mirror plane, which is perpendicular to the in this particular case the xz plane. So, mirror is cutting through this. So, we have this side is mirror image of that side. So, it is like I put my left hand here and my right hand here, and these now are related through this mirror plane. So, you see that the overlap of the objects will occur that way only if we now take this image and take the image which is the left hand. So, the right and left hand define what are known as enantiomorphous objects. So, the objects, in fact, these two are not going to be identical otherwise. See, nobody's left hand is identical to anybody's right hand, then it will be a terrible issue, is it not? If both of them are identical and they are by real space, they are related to each other, then our hands will be in a different, I do not know what orientation I have to show you, but it will not be like that. So, it has to therefore have the two objects, therefore, my left hand and the right hand are enantiomorphous objects. So, the symmetry that is associated with a mirror is enantiomorphic. What do you think is the symmetry that is associated with the center of symmetry? This should also now be an object where the right hand side, this side of the object is now going to minus x minus y minus z. So, when there is a change of value of x, y and z, all three changing from x, y, z, then also you have an inversion. So, the inversion is also an operation where the object can be also not necessarily, and in fact, it is not enantiomorphous object. So, enantiomorphous objects are very special, and therefore, the enantiomorphous behavior in the arrangement of molecules will also be different. And this happens in case of many of these amino acids, particularly the naturally occurring amino acids. The naturally occurring amino acids are have a rotation, the optical rotation, they have their levo or dextro-rotatory, and most of the naturally occurring amino acids are levo-rotatory. And therefore, when you arrange these molecules into a protein, the structure of the protein always can never go into a centrosymmetric system. It has to go into a non-centrosymmetric system because it has to have the so called enantiomorph behavior. So, the objects that compound a protein will be enantiomorphous objects, and this is something which is very interesting in biology, and in fact, the most of biology is a matter of fact consequence of the presence of enantiomeric objects in protein structures. That important point is something which will clinch the whole issue. That is, suppose you have, let us go back to the center of symmetry, or for that matter we can go to this mirror. So, in the case of the mirror operation, we take x, y, z to x minus y minus z. So, the point from here went to the other point. Now, suppose I operate a mirror plane again on this fellow x, y bar z. What will happen? X, y bar z will go back to x, y, z. So, x, y, z and x, y bar z are the two equivalent points, which are related by this symmetry operation. We call this as the symmetry operation. They are related by the symmetry operation. These are the two equivalent points, and no other equivalent point exists in this diagram for this diagram. That means x, y, z goes to x, y bar z and x, y bar z goes back to x, y, z. So, the whole this thing, the closing, it is referred to as a closure property. And in this brings in the issue of group theory. So, in group theory we call such operations as operations of a group. Now, there are various ways in which we can approach this problem. We can go into a conventional group theoretical way of doing things, but then I thought that it is not the way we will go about. Instead, we will keep this in mind that when we have these equivalent points, operation of the equivalent point once again will take it back to the original, depending on what kind of situation we are in. If there is only one mirror plane operation, x, y, z goes to x, y bar z and x, y bar z goes back to x, y, z. Now, this kind of a thing will therefore close the whole issue. That means, we cannot have any more objects. If I have an object here, these two objects only are there in this particular unit cell. Beyond that, we cannot have any more objects. The next unit cell is only a translational periodicity repeated thing, and therefore, this will now repeat itself in the next unit cell. It will repeat in the both directions A and B, and therefore, the existence of points x, y, z and x, y bar z, they define such a situation in mathematics is referred to as a group. So, they define a closure property, and therefore, this defines a group property. So, the points now belong to a group. There is a clear cut mathematical procedure through which we can understand what is group. There is a group theoretical principle, and we can design now the so called methodology for using this group theoretical information to identify what are known as point groups and space groups. In fact, the presence of point groups and space groups, we will bring it in a totally different context and then relate what we have seen in these diagrams once again to whatever we have achieved so far. So that you get a one-to-one correspondence without going into the rigor of mathematics which is involved in group theoretical methodology, even though that is probably not the method to follow the group theoretical behavior. In this particular case, particularly for chemists and biologists, it will be very useful to understand what we are doing in terms of these pictures, and also now eventually when we do the point groups and space group, how we derive these point groups and space groups rather than how mathematics arrives at that. Because the mathematically deriving thing is straightforward and very easy from the mathematics point of view, but from the understanding point of view, the way we are going to do in terms of group theory and the particularly the point group derivation and space group derivation will be a better way of understanding the three-dimensional architecture in molecular crystals, crystalline materials which have molecules or ions or whatever. It is easier to get a picture of that. Right. So, we saw the glide plane. So, what is important here is something which we defined already, we have been talking about it, but we have not put it in a real nutshell. So, what it is like, as I always tell in my regular class, what we have done today in the last few classes, I think it is now the class number 3 as far as time is concerned. So, in the last 3 classes is to get the alphabets. You see, it is something like developing a grammar. We are now trying to develop the grammar of crystallography and the grammar of symmetry and structure particularly. So, to develop the grammar, we are now looking at various alphabets. So, what we have got so far is in terms of the definitions of close packing, the presence of symmetry in 2-dimensional, and eventually we will extend to 3 dimensions. And we have used the 2-dimensional drawings of Escher to get a feel for what are the types of symmetry elements that can be there to describe the 2-dimensional motifs which are already displayed. So, in this particular context, we have been talking about the definition of what we have been referring to as the unit cell. The unit cell is something which repeats itself in both the directions. In this case, it is 2-dimensional. So, this marking which I have done in red will define the so called unit cell. That means, whatever is there inside, which is now atoms and molecules and so on, instead of these objects, whatever is there inside this box will repeat exactly the same way in the next box. It does not mean that I have to fix the origin here, I can fix the origin wherever you want. So, it is like the window frame. If we want to fix a window frame and in a building, all the windows are identical, the size, the dimensions of the windows are identical. So, we have to now generate frames. Now, the frames which we generate are the unit cells. So, we can take the unit cell, fix it to this window on the right, window on the left, window in the back, window in the front, because as far as the dimensions are concerned, they remain the same. So, similarly, unit cells therefore can be defined in such a way that they are like frames. So, we can move this along anywhere in the 2-dimensional space, it will fit exactly the symmetry that is required for this 2-dimensional motif. So, that way we define the unit cell here in terms of length. Now, I can call this as 0. The 0 or the origin can be anywhere in this diagram. So, we have decided to fix it there, then this distance will be a, 0 to a along the x axis, x direction, and in the y direction we see that this is b. Now, if we go back to the threefold case here, you see, suppose I call this as 0 and this angle is very crucial now. So, if these are the vectors, so this vector is now a and this vector is now B. Okay. So, effectively what happens is this now defines the unit cell 0 B and 0 A. You see that this is not, if we take this along the x axis, the 0 A along the x axis, B need not be along the x axis. So, the presence of the B will be in such a way that we have to now define the direction of B. It is not with respect to the 90-degree angle, and so this becomes an issue in case of 3-fold and 6-fold. It is not an issue in case of the 2-fold and the 4-fold. Okay, so remember this, we will see why it is so important later. So, in this particular example, coming back to the definition of a unit cell. So, we define this unit cell as a repeat unit. It repeats itself in 2 dimensions to describe our entire motif. So, the unit cell is drawn in all other repeating wall patterns. So, this is just to show that the unit cells can be drawn for all the diagrams we have shown in the now coming to the last part of today's this particular class, we will see that the 2 dimensions can be extended to 3 dimensions, because now we are in a situation to go towards 3 dimensions. So, just like we have the concepts built in 2 dimensions, we extend this to 3 dimensions, and we therefore have a direction A, direction B and direction C. Remember, A, B and C need not always be rectilinear coordinates, they need not be at angles of 90 degrees, depends upon the symmetry. If the symmetry allows for A, B, C to be at 90 degrees with respect to each other, then only we can have the unit cell definition. Okay. This is very important to remember at this moment. So, this produces now a box. So, the box can be like this with all 90-degree angles, and if A is equal to B is equal to C, alpha, beta, gamma, the angle between these A, B and C are 90 degrees, then we call this a cube. So, this will be one of the possible unit cells which we can have in a 3-dimensional description of the crystal structure. So, crystals can grow into cubic cells. We will see how many possible cells are going to come in the next class and in what way they appear, and the consequences of how the angles play a very important role, and the concept of vectors. That means, we are now depends upon where the origin is defined, the concept of vector A, vector B and vector C, the way in which we define A, B and C, and the angle, interaxial angle between them becomes crucial to define the crystal geometry. And the 3-dimensional unit cells which will develop cannot be all kinds of unit cells, because it has to have the information about the symmetry we have understood. So, combination of symmetry and the requirement of the 3-dimensionality in the unit cell which preserves this symmetry, it will allow only a certain set of possible unit cells, and that is how we end up with 7 crystal systems. Okay. So, today's class will end at this particular moment and we will go further. Now, before I go further, I just thought I should give you 3 reference books. One is the book of Fundamentals in Crystallography. It is an IUCR text, and this is by Carmelo Gay Cavallo, and some of the contents of today's talk is taken from there. The Escher's diagram and the way in which it develops and so on is my own imagination, and so it is dependent upon how you view it and how one views it. So, I thought that that would be the best approach to give you the concept clear, and in the next class we will go and try to understand the concepts of how to represent these symmetries, how the symmetries accumulate, and we now then go into the aspect of what we call as point group symmetries. So, the next book is by Jack Dennitz. It is X-ray Analysis and Structure of Organic Molecules. This is a book where you will find some very basic understanding of the X-ray diffraction theory, and then how it refers to the molecular species. The fundamentals of crystallography will cover overall all the aspects. There is another book by Stout and Jensen. This is a book on X-ray structure analysis, practical guide. I did not write it down here, but It's X-ray structure analysis, a practical guide, and that book is a bit ancient, but at the same time it gives us the required basics. So, what you will see in the coming classes will be that I will be using these concepts in and out, on and off. So, books of these books will be referred to once in a while, and whenever I refer to that I will mention I have taken it from this particular book, so that when you have to practice what you want to do in future with this course, then and you are got hold of these books, it will help you to find out where we are now referring to at that particular moment. Okay. So, I think we will stop here for today. Thank you.